All right. So I'd like to continue the discussion that we started last time on this simple model of electronic states in an extended system, in an infinite system made of an infinite chain of atoms separated by A, each one bringing one atomic orbital. We have constructed a solution of this model with some approximations, with the same approximations we used to discuss the solution of the covalent bond problem with only two atoms. And let me just summarize here the form of the solution. So the solution psi is the sum over I of e to the I q I times phi of, let me write it explicitly now. Okay, I'm just writing explicitly what we wrote at the blackboard somewhere there last time. That is that the wave function is the sum over some coefficients which we determine to be e to the I q I times the atomic wave function. I think we call it 0. Fine. No, yes, you're right. Yeah, we put the not on top, yes. And instead of putting I here, I'm writing explicitly what I mean by that. It's the atomic wave function centered at site Ri. Okay, so, and Ri is AI. So it's the position along this one-dimensional line R. We are in one dimensions here. We forget about the extra dimensions. We're just in one dimensions. This is the solution that we determine. Actually, let me put explicitly here a label to identify that this is the solution with quantum number q. We said that there are infinitely many solutions which are labeled by this number q. Q is a real number. And in fact, q, we said, we can restrict q to be between minus pi and pi without losing anything. Yes?
Why we usually use periodic interval?
Where? Here for q? Oh, okay. I mean, I need to go back to the beginning. I mean, that's what we want to solve. We want to solve the problem of an ordered array of atoms. You may, of course, wish to solve the problem of an arbitrary arrange of atoms. Well, this is not going to be easy to do. So the theory we are going to develop works only if we can assume that here there is translational periodicity, okay, translational symmetry. Now, I have to go back to my first lecture where we discussed that solids are in general of arbitrary shape, of arbitrary atoms, can be in principle arranged in arbitrary fashions. But, I mean, to a large extent, solids are made of ordered arrays of atoms, aggregates of atoms. For example, this one is in principle a disorder, but if you look with a microscope at the micron level, you will start seeing collections of ordered arrays of atoms. And this is what we're going to describe. Okay? This, of course, doesn't mean that there are systems, actually, I mean, many systems in which the atoms are not arranged in this fashion. Well, there's nothing we can do in those cases. You have to simply try to work out the solution in a more complex way. Okay? So the argument, I mean, actually, this is a very important point, and let me stress it once again. Solids are not, generally speaking, only periodic systems, but we argued that they are to a large extent made of periodic systems, if you look at the small scale, at the microscopic scale. And if they're made of periodic systems, at least over a large range of space, then our theory allows us to solve the problem very efficiently. Okay? So, in some sense, we have a very powerful theory that allows us to solve periodic systems. If they're not periodic, we will have to somehow assume that the system is close to periodicity, because only in those cases we are able to solve the problem. Or, I mean, which is the truth, that the system is made of grains, which within the grains are periodic, outside they're not periodic, I mean, between one grain to the other one. But then we also argue that the number of properties of a material don't really depend on the way the grains are arranged. They only depend on the fact that they are arranged periodically within the grains.
So for the system which are not periodic, we can solve the problem by using the periodic system and do some arrangement.
Yes, we can approximate a solution of the non-periodic system, as long as, of course, the system is close to a periodic one. Let's say, again, aluminum is not periodic over a large scale, but if you look at the micron scale, it is periodic. There are grains which are perfectly ordered crystals, microcrystals. Then, of course, the next crystal is arranged in a totally random way with respect to the first one. So overall, it's not periodic. If you sit here and you try to apply translational symmetry, you get here, it's not, I mean, it doesn't apply, of course. But within a micron of length, it does. And a number of properties that aluminum has can be explained by just looking at the properties of the system within the micron scale. We don't need to go to really make sure that there is periodicity all the way from here to show, say, whether aluminum is conductive or not. If aluminum is conductive, it really depends on the way the atoms are arranged at the microscopic scale, not at the macroscopic scale like this. And at the microscopic scale, most systems are periodic. Not all of them, of course. Glass is not periodic, not even at the microscopic scale. Okay? The only regularity that glass has is that if you sit on, say, on a silicon, you'll see 4 oxygens around yourself. But when you go beyond that range, which is an angstrom or so, a few angstroms or so, it's completely disordered. Okay? So no way we can use this theory for glass. But, okay, glass is an exception. And we're going to treat it. Actually, we're not going to treat it at all during our classes. Okay? Fine. So this is an infinite set of solutions labeled by Q. Q can take these values. It can also take values outside this range, but as we argued last time, there's no need to go outside, because if we go outside, there will be a solution inside this range that is exactly identical, both in energy and in terms of wave function. Good. And the energy for this eigenfunction as a function of Q is E naught plus delta E naught plus 2t cosine of Q. All right, so that's our main result of last time. I'm just summarizing what we discussed and actually writing explicitly the form of the wave function here, which last time we kept in an implicit form. Okay, allow me now to make a slight change of variables, very small one. What I'm going to do is here, divide this by A and multiply by A. I'm not changing anything, but what I'm extracting out is AI, which is Ri, by definition. And let me now call this object here, instead of Q, let me give it the name K. I'm just changing variable. A is a constant, is the distance between the atoms, so I'm going to call it K. So I'm now going just to rewrite the same thing just in terms of K, it's obviously. So instead of labeling the solutions in terms of this number Q, I'm going to label them according to this number K. It's the same, just that it's scaled by factor of A. And the solution now as a function of K is E naught plus delta E naught plus 2t cosine of K A, right? Because Q is K times A. I'm now changing variables only. I'm not doing anything particular. And of course, if I change variables, I'll also need to remember that the range of possible values for k is now this one. This sounds probably a little bit more familiar to you at this point, right? I guess you have seen these kind of expressions before, and you start to realize that there is something, some analogies that we already discussed a few lectures ago, where we introduced the Brillouin zone. But I'll discuss this now in more detail in a moment. So let me now plot again this function. I'm just replotting. Let me now do it properly. Now I'm putting E naught plus delta naught as a negative number. This is minus pi over a. This is pi over a. We're now as a function of k. And this is the energy as a function of k. Of course, it will continue this way, but we just stop between minus pi over a and pi over a in terms of k. Notice we change variables, so it's no longer pi, but it's pi over a now. And that's the energy as a function of k. The only difference with respect to last time is now I shifted the value of E naught plus delta naught to bring it to a negative value, which is what you argued was correctly the... All right. Now, the first thing I want to discuss now is there are several things that we're going to discuss about this result. The first thing I want to discuss is electron counting, how we're going to fill these states. As we argued last time, we need to now put the electrons in this energy spectrum, and we cannot really say that this is the ground state, the lowest energy value is the ground state, because we have an infinite number of electrons to place in this infinitely many states. So we need to handle infinities in order to be able to say where do the electrons go here. Do they all cluster here? Do they fill the whole spectrum? What do they do? We have an infinite number of electrons and, however, also an infinite number of states, because this is a continuum of k's, of possible states. So we have two infinities and we need to play with infinities. So we need to do it properly. Handling infinities, as you know, is not straightforward. We need to do it properly. And the best way to handle infinities is to handle large numbers and then send the large numbers to infinity. Okay? So we're going to now do the theory for a system of very large size, and we are going to then send the size of the problem to infinity. This will ultimately, if the limit converges, of course, that will give us the answer to our problem. Now, the way we're going to do it is not the obvious way. Well, the obvious way to handle the problem would be to say, okay, we have, at some point we have surfaces, like we have grains in crystals, and so this system is truncated. So we have a system of very large, actually let me replot it here for simplicity. So we have our atoms here. And the obvious thing to do, of course, would be to say at some point, well, we have a surface. The system stops. Okay, there is a length, a chain of atoms, and there is an end, and a beginning and an end. Now, this is obviously the more realistic way of cutting a system, and then perhaps, so we have a total length L here, which is perhaps n times A, where n is a very large number. That's the obvious way and more realistic way, more natural way to say that we have a large system, not an infinite system, but a very large one. And we could then think of sending n to infinity. Right? If we send n to infinity, we are dealing with an infinite crystal. Now, the problem with this is that it's not trivial to solve the problem of a chain where you truncate the ends. It creates a number of problems. I mean, there are, for example, these poor atoms here, they have no partners to the left side, and this atom here has no partner to the right side. So you need clearly to handle these two atoms in a different way. Actually, even this one, in our approximations, is fine, because in our approximations, this atom interacts only with this one and with this one. So it doesn't recognize the fact that there is another atom here, because we have made the approximation that we are neglecting second nearest neighbors. But in principle, this is just an approximation. So even this one might feel in principle the effect of a second nearest neighbors on the other side, right? So it can be done, but it's mathematically very difficult, because we have to handle different situations in the bulk and close to the surface, quotation marks, of this one-dimensional system. Now, the way we're going to solve it now is to say, instead of saying that here we truncate the surface, we're actually saying that the left partner of this one is this atom here. Okay? So we're going to impose periodic boundary conditions, fictitious periodic boundary conditions, between the two edges of our very large grain, a very large system. Not infinite system, but very large system. Okay? Notice these have nothing to do with the periodicity of the system. Periodicity of the system is something else. So the system says that you can translate the system periodically and nothing changes here. Here we're only saying we're adding something fictitious, totally fictitious. We're just saying that this atom, if you continue to the left, you're actually going to find this atom, and so on and so forth. Now, this is fictitious, but you all agree with me, I guess, that if I send n to infinity, these fictitious periodic boundary conditions are again irrelevant, because we're actually talking about something that is infinitely away from the bulk and infinitely away from the bulk on the right side. So the fact that this atom is actually connected to this one is irrelevant if the system, if this chain has an infinite length. Okay? So we're not going to truncate the system, but we're actually going to make it periodic over this very large periodicity given by very large n and a very large length Na. This kind of trick goes under the name of Born-von Karman periodic boundary conditions. Okay? It is a trick. It is a mathematical trick. It's nothing to do with the physics. It's a mathematical trick that allows us to work with a system of finite size, because we have a finite number of atoms, capital N, which we will then be sending to infinity. And at the same time, it allows a quick solution to our problem without having to deal with the truncation at the edges. So what happens if you apply this particular Born-von Karman periodic boundary conditions to our wave function? Well, if we apply these conditions, what we need to impose is that psi k of r plus n times a is equal to psi k of r. That's all we have to do, right? We have to say that our wave function, when we translate it by Na, which is the length of this segment, just goes back into itself. Again, it's something artificial. It's something fictitious, something artificial that we're just adding for the purpose of being able to count the states and the electrons. If we send n to infinity, this is totally irrelevant, because we are talking about an equality between wave functions, points located at infinite distances. So it's totally irrelevant for the physics of the problem. But if n is finite, it allows us to count numbers, count states, because we are going to handle with a finite number of atoms and a finite number of electrons. Okay, so let me explicitly impose this onto these functions. So we have sum over I e to the I k Ri phi of phi naught of R minus minus Ri. Let me write that as AI plus NA. Okay, I'm writing Ri as AI plus Na. And this must be equal to sum over I e to the I k Ri phi naught R minus AI. Okay? I need to impose this. Let's see what we get if we impose this equality. Now let me define I prime as I minus n. Oh, sorry, I should have also written this one as AI. Let me find I prime equals to I minus n. Sum over I of e to the I k a I prime plus n, right? I is equal to I prime plus n, phi naught R minus a I prime. Okay? Or I'm continuing to expand the left-hand side of the equation. I'm actually now taking out this n because this IKA n is a constant, so I can take it out of the sum. Okay? But whether I sum over I goes from minus infinity to plus infinity. Or if I sum over I prime also goes from minus infinity to plus infinity. It's the same. I'm just changing the index over which I'm summing something from minus infinity to plus infinity. Right? So here I can say, well, I can sum also over A prime. That's the same. The two indices will anyway go from minus infinity to plus infinity. So there's no difference. If I sum over I or I sum over I prime, I'm going to cover all possible integers, all possible values of I prime between minus infinity or plus infinity, and all possible values of I from minus infinity to plus infinity. There's no difference. I'm just changing the origin of my index. But this object now, if this is I prime, this is identical to the right-hand side, right? The only difference is that the index is called in a different way. I prime here and I, but the index, a running index, I can give it any name I like, as long as it runs over the same number of values, range of values, which is minus infinity to plus infinity. So this object is the same as the right-hand side. But if this object is the same as the right-hand side, and I want these two quantities to be equal, this one must be 1. If I want to impose this periodicity, okay, this one must be 1. Because this object is the same as the right-hand side. If I want them to be equal, this and this must be 1. Okay, so imposing these boundary conditions imposes k to take selected values, not all possible values between this possible range, but it forces k to take values equals to 2 pi over a 1 over n times an arbitrary integer, right? Only in this particular case will this be 1. If k a n, k times a times n is 2 pi, or 2 pi times an integer, which is what I'm writing here, right? K a n is 2 pi times an integer, m. But k, according to my initial theory, had to be restricted to minus pi over a and pi over a. And now I'm just imposing that k, in addition to this, must also take these particular values. Notice here, this is actually, I can also write it as 2 pi over a m over n. And remind that n, capital N, is a very large number. So essentially what I'm doing here is I'm discretizing k in small bits, in small slices, the width of which is 2 pi over a divided by n, by capital N. Okay? So in other words, if this is 2 pi over a, right, the total length of this is 2 pi over a, for example, okay, what I'm doing here, if n is large, is to select values slicing this object in very small slices like that, and accepting only specific values of k. The width of this is 2 pi over a 1 over n. And of course, m, at this point, if I want to stop here, m, the integer, can only go up to n divided by 2, right? Because if m is equal to n divided by 2, then this becomes pi over a. So that's the last one. So this point here will be m equals to capital N over 2. I'm assuming that n is even. Okay? N is large, but I can make it even. Similarly, this point here will be m equals to minus n over 2. So in total, I will have capital N slices in this segment. All right, so what I've done, if I impose this periodic boundary conditions, again, artificial periodic boundary conditions, is to essentially force k to take discrete values. Not all of them, but discrete values. And if I make n large enough, this grid is going to become finer and finer and finer. Essentially, it becomes a continuum. Okay? But now I can count the states, because I have only a finite number of states that I need to handle, because only these values of k are allowed, which means only selected values of the energies will be allowed, the one that correspond to that particular value, those particular values of k. Right? Now I'm probably not counting exactly the same number of points, but anyway, you have to think that each one of these points will have its own corresponding energy. So not all the energies are allowed, only a discrete subset of this curve are allowed, and they're the ones corresponding to the discretized value of k, which I introduced as a consequence of this, of imposing these periodic boundary conditions. Of course, at the end, I will let n go into infinity, of course. But let me assume that n is now large, not yet infinitely large, and let me now count the states. All right, so how many states do I have here in my problem? with this discretization with these periodic boundary conditions. The total number of states will be given by the total number of Ks, slices. And that number of slices is, as we said, n, right? So we have a total of n, capital N, possible energy values, states. There will still be some degeneracies because, for example, this one will always be degenerate with this one. So we always have a twofold degeneracy here. I mean, that's natural. Nothing wrong with that. But we have a total of n, capital N states. How many electrons do we have now? Well, it depends on the problem. But if here this is, say, for example, a chain of hydrogen atoms, that is, our orbitals are the 1s orbitals of the hydrogen atom, for example, then each atom brings 1 electron to the problem. So if we now go back to the system we are describing with these periodic boundary conditions, how many electrons do we have here? How many electrons do we have if each one of them is a hydrogen atom? N electrons. So we have n states and n electrons. How are we going to fill these n states? With n electrons. We have to start from the lowest one. And we have to remember that here spin for us is not, I mean, the Hamiltonian does not depend on spin. So each state can accommodate 2 electrons, right? And spin up and spin down. So we are going to fill up our states. Okay, the first one, 2 electrons. Then 4 electrons, 6 electrons, 8, 10. Okay, let's continue, right? If we fill up the whole system, how many electrons would we need to fill up the whole spectrum? 2n, because we have n states and 2 electrons per state. But we only have n. So where will we stop? Halfway. And where is halfway? Here, right? That's, I mean, it is a periodic, it's a sinusoidal function, so halfway means that we stop here. All right? So these states will be filled, and these states will be empty in our problem. Up to this point. And the other states will be empty. Now, sending n to infinity now doesn't change qualitatively the picture. It just makes the separation between these states finer and finer and finer, but there's no reason why our discussion will change if n is infinity. It's just, I mean, you're just making this set of this grid an extremely fine one to the point that it becomes a continuum of points, but the fact that all these states are filled up to halfway and all the other ones are empty remains true, of course, for an arbitrary n, and therefore also for n going to infinity. Okay? Now, a couple of remarks about, actually one main remark about the energy. You may remember again, let's go back to the covalent bond, right? In the case of the covalent bond, we had 2 states, we had 2 electrons, we filled the lowest one of the 2. Here we have infinitely many states, infinitely many electrons, yet if each atom brings 1 electron, we are going to fill half of them and keep half of them empty. Okay? So somehow qualitatively the picture hasn't changed. The only difference is that now instead of having 2 discrete states, one of which was filled and the other one was empty, the bonding state and the antibonding state, here we have a continuum of states, the lower half which is filled and the upper half which is empty. Okay? So qualitatively the picture hasn't really changed too much with respect to the covalent bond before. We're simply transforming, we're simply dealing with an infinite number of electrons compared to the finite number of electrons that we had, actually 2 electrons that we had at the beginning for the covalent bond. Is there a question? Ah, yes.
When I see the solution of the wave function,
Mm-hmm.
it looks like something which is moving.
It looks, okay, if you look at this solution, it looks like that it's moving. Well, first of all, there's no time here. So I don't understand what you mean by moving. Okay? There's no time. So this is just a static wave function for the time being. It is a wave, however, and I'll come back to that in a moment about this wave-like nature of the solution. But we'll come back to that in a second. Okay. What I wanted to highlight, however, is that here. No, sorry. I will come back later on when we discuss the three-dimensional system. No, I think it's done for the time being. So we've solved almost exactly with a few approximations a simple problem. We've been able to find this peculiar solution. We've noticed that we have to fill only half of the states and the other half must be left empty. Of course, if each atom was bringing, instead of 1 electron, was bringing 2 electrons, then we would have a total of 2 n electrons, and we would have to fill this continuum completely. So all the states would have to be filled. So this way of filling the states depends on the number of electrons that each atom brings to the system. So in other words, what we can say is that a full band, okay, let me give it a name now to this. So what I mean by that, this is the name that we give to this object is not a line, is not a spaghetti, but it's a band. So we start using terminology that we'll become familiar with later on. So a band contains a number of, can contain a number of electrons, which is up to 2 electrons per atom or per cell if we are dealing with a complex system. So I'm now going to make a statement which is more general than the one we derived, but let me make it now and we'll come back to that. The number of states in one band, number of electrons. No, let me phrase it properly. The maximum number of electrons. The maximum number of electrons in a band is equal to 2 electrons per atom. Or, if we have a more complex system, not just 1 atom per cell, 2 electrons per unit cell. Now, this is actually a more general statement than what we've derived mathematically here, because here we derived the mathematical for a very simple system. We will see later on, we will not prove it, but we will see that this is a very important statement. We will have to keep in mind that the total number of electrons that we can place in a band, if you want to fill it, it's 2 electrons per atom or per unit cell, per repeat unit of our system. Here the repeat unit is just 1 atom. If it's a unit cell, we will have to consider the whole unit cell. Yep.
Is it possible, I don't know, maybe, I think it could be another idea. Okay, instead of thinking like a chain of, certain length A, and then
Yes.
relating the limit to go to infinity,
Yes.
we consider a circle.
Yes. So your argument is that instead of considering a length, yes, okay, a chain of length NA, why don't we bend it and consider it as a circle?
And then,
Okay.
instead of translating, now we use the rotation of
The rotational property, and then you say if the circle becomes infinite, the radius becomes infinitely long, it is essentially. Why not? Yes. Why not? Yeah. Although, I mean, in principle, you can abstract yourself and deal with this problem, I guess. This is just because you want to see something real. But I mean, I can always live in a world where this is true, where if I jump from here to the left, I end up here. Okay? It can be a Cinderella world or something like that. I mean, we are theoretical physicists. We are not.
Because, I have here pi minus pi something, so
Sure. Okay, sure. I mean, you can think of it as a circle that in the limit of very large radius becomes a line. Yes, why not? It's the same, of course.
Yeah, in the same line, I think it does not work, because when you make that a circle,
Yep.
there will be instances of curvature. So
Yes.
the instance that you're considering is no longer
Yeah,
A.
that's right, yes. So this is a very good argument. I mean, if we deal with the infinite system, yes, I mean, we all agree that it's the same. But if we want to study the finite system, then we have to study a system in a circle, and so we have some issues about how we're going to describe the curvature of this finite system.
yeah, because we let the radius to go to infinity. And then
Sure, in that limit everything is fine, but in the finite limit you would have to be able to describe a system which is curved, while here we deal with a system which is flat.
Yeah. For finite case, it doesn't work because even when we study this thing, we neglect the nearest neighbor interaction. If we consider
Right, okay, fine, that's fine. No, it's I mean, good observations. They are both okay in some sense, right? They're both compatible with our purpose. All right. Let me make the final statement about this wave function. Actually, it's very similar to this consideration here. And don't ask me to repeat it. I mean, I'm just going to, I'll do it very quickly. So I take my wave function, and I translate it by an arbitrary repeat unit, an arbitrary one. Okay? So RJ, that is, we know, A times J. So I take my unit cell and I just translate it by some J units. What's happening if I do that? Don't ask me to repeat it, right? I can just replace J with N. Here I go. Okay, so what I get is e to the I k a j times the same wave function, that is psi of r. Okay? In other words, if I translate my wave function by an arbitrary repeat unit, I get back to my wave function, but I acquire a phase which is proportional to the length of my, number of steps, how many steps I actually moved. Okay? This is, of course, equivalent to saying that my wave function is made of a periodic part times a phase, which is what my wave function acquires when I move it to by a certain length in space. These two statements are actually equivalent. When I say that if I translate my wave function, it goes back to itself and acquiring a phase, I'm just saying that the wave function is a periodic part times a phase. Right? The periodic part is what remains, and the phase is what is acquired every time I move by a given amount of steps. So this is actually the same. It's the same statement. And this is periodic. So there is a component that stays the same when I translate it, and a component that acquires, and this trivial thing part that acquires a phase. Now, this is exactly Bloch's theorem, as you may remember if you have seen it already. But I just wanted to show you, or actually this one, this is also another way to express Bloch's theorem, that when you translate the wave function, it acquires a phase. So, what I'm going to do now is I'm going to generalize all the statements that we've obtained based on this oversimplified model. I'm not going to prove them. We've proved them for this particular model, very simple model. But I'm going to state them. I'm going to highlight some statements that can be made and are very general about it, about solutions of periodic problems, periodic electronic problems. Okay, so what I'm going to I'm now going to make a number of statements, most of which I'm not going to prove, but if I don't prove them, we prove them in this particular example. Okay. So I'm now going to make a number of very general statements. So the first statement is, what is the Hamiltonian I want to discuss? The Hamiltonian I want to discuss is an Hamiltonian V of r, and I'm now going to be general. It's a three-dimensional Hamiltonian, which has a very important property. V of r plus Ri is equal to V of r, where Ri belongs to, actually for any Ri belonging to a given Bravais lattice. Okay, so I'm going to generalize my statements in 3 dimensions. I've been dealing with a one-dimensional Bravais lattice before, right? It's a periodic system with atoms arranged in regular positions at distance a in 1 dimension. Now I'm going to generalize the problem to 3 dimensions. I'm going to have an electron, or actually a number of electrons, subjected to this potential, to this Hamiltonian. And the potential that the electrons feel is periodic, like the one that our electrons were experiencing in the one-dimensional case, which was a sum of Coulomb potentials repeated periodically. So now I'm going to be very general. I'm just saying I just require my potentials to be periodic with the periodicity given by the Bravais lattice, a Bravais lattice, something. So I have to give you a Bravais lattice, and I'll tell you the potential is periodic with this periodicity. I have an Hamiltonian with that potential. What are the properties that the eigenfunctions of this Hamiltonian have? So the main property that the eigenfunctions of this Hamiltonian have is that there are 2 important properties. The first one is that solutions psi of k of the problem, that is functions that satisfy this property, right, eigenfunctions of our Hamiltonian problem, can be classified according to a quantum number k, which is now a 3-dimensional quantum number, not a 1-dimensional quantum number like here. We are in 3 dimensions, so this k becomes a 3-dimensional quantum number. Now, you have certainly noticed that this region minus pi over a and pi over a, and the fact that we had periodicity with periodicity 2 pi over a, in 1 dimension, this is actually the Brillouin zone of a 1-dimensional system. And 2 pi over a times n are the reciprocal lattice points in one dimension. Okay? So our solutions were periodical in a space. Actually, let me look at this one here. Are periodic functions in a space which is periodic with a periodicity 2 pi over a, and 2 pi over a is exactly the periodicity of the reciprocal lattice in one dimension. Not only, but this range of k's corresponds to the unit cell of the reciprocal space. We didn't introduce this, say, terminology before, but now it becomes clear that this was exactly what I'm just saying. This function has a periodicity 2 pi over a, n, which is the periodicity of the reciprocal lattice in one dimension. This is the unit cell in one dimension. So I can rephrase these statements by saying that solutions can be classified according to a quantum number k. Solutions are periodic with periodicity given by the reciprocal lattice, and solutions can be classified according to a quantum number k whose values can be restricted to belong to the unit cell, because elsewhere they are periodic. I don't need to go outside, because what I will find outside is exactly what I will find inside the unit cell, one unit cell, which I choose to be the Brillouin zone of the reciprocal space. I'm just rephrasing with a different language something that we've already done and calculated. Now, keeping in mind that this range here is exactly the Brillouin zone in one dimension, and that the periodicity is 2 pi over a, with 2 pi over a is exactly the periodicity of the reciprocal lattice in one dimension. There's only one in one dimension, right? Reciprocal lattice. So I'm going to generalize now these statements in 3 dimensions, and I will say, and I will just state them, I will not prove them, and I'm saying that if I have this problem, periodic problem, solutions can be classified according to the quantum number k, that is, solutions of this problem with h periodic can be classified according to a quantum number k. Solutions are periodic in k with periodicity given by of the reciprocal lattice, and therefore I can restrict my k to belong to the Brillouin zone. Okay? I'm not proving this statement, but we've shown that it is true in the case of a one-dimensional problem. And you have to trust me. This is true also for the three-dimensional problem and the more general potential, as long as the potential is periodic. That is, the electrons feel the same potential in all the unit cells. Again, k is a quantum number to classify the solutions. This is the statement, I mean, what we mean by solution of the problem. And k, the solutions are periodic in k, and k, therefore, can be restricted to the Brillouin zone, to the unit cell. We don't need to go outside. But there's another property, which is also extremely useful, and this is the one that we observed here. Namely, psi of k can be written as uk of r, where this is a periodic function. Periodic, it's a function of r, right? As a function of r is periodic, not as a function of, it's also as a function of k, but the important statement now is that as a function of r. Periodic as a function of r, and therefore the periodicity of the Bravais lattice. Times a phase okay? These two statements are essentially Bloch's theorem. It's a theorem. It can be shown mathematically. We're not going to prove it. It is something extremely important in solid-state physics because it gives us an important starting point to discuss and to determine electronic states for a periodic system. First of all, it provides us with a very good quantum number to classify states. Secondly, it gives us an important property of the solutions of the periodic Hamiltonian. Now, let me elaborate a little bit more the statement here. What I'm saying here is that the wave function contains a periodic part and a phase. Now, this Hamiltonian here has this kind of translational invariance. So in the language of quantum mechanics, it's an Hamiltonian with a symmetry, a very specific symmetry. It's a translational symmetry. Now, if a Hamiltonian has a symmetry, do the corresponding wave function solution of that Hamiltonian have the same symmetry or not? Right. Are you all familiar with this statement? Let me ask your friends. So the question is, suppose you have an Hamiltonian with a given symmetry. Suppose you have an Hamiltonian which is, say, has a rotational symmetry, spherical symmetry. The hydrogen atom, for example. Right? It's an Hamiltonian with spherical symmetry. Do solutions of that Hamiltonian share the same symmetry as the Hamiltonian itself? Do they or don't they? Who is for yes? Who is for no? Raise your hands, come on. Who is for no? You're allowed to raise your hand if you wish now. Who is for no? Nobody's for no? You're all for yes? So, if I give you an Hamiltonian with spherical symmetry, do wave functions, solution of that Hamiltonian, share the same symmetry? Yes? Yes? You're all for yes? No? Something even simpler, a square well. I hope you're all familiar with a square well. You have a square well. I can put the center of the origin here, right? You have a square well. So this is V of x. This potential clearly has inversion symmetry in one dimension, right? Reflection symmetry. Question: do solutions of this problem have reflection symmetry or not? Do they have them? Okay, ground state. How does it look like? Oh, suppose it's infinite. Okay, let me take infinite well. Ground state, like that, right? First excited state. Okay, very good. Does this function have inversion symmetry? No. If I reflect it, it goes into minus itself. It doesn't have inversion symmetry. Okay? What about the hydrogen atom? Does the 2px state, you know p states, px is the one, the orbital oriented along x. Does that state have spherical symmetry? No. Right? It doesn't have spherical symmetry. So, solutions of a given Hamiltonian with a particular symmetry, they don't generally share the same symmetry. They share, however, something else. Okay? I'm sure you have seen this in quantum mechanics, right? For example, this one, this particular wave function, it is true, it is not. It doesn't have inversion symmetry. But if I apply this symmetry, it goes into minus itself. Okay? So there's parity, okay? So in other words, they're not exactly sharing the same symmetry, but they are sharing something. I mean, they have some properties. in particular, in this particular case, you have to multiply the wave function with the eigenvalue of the parity operator. I don't want to go into the details of that. Just go back to your quantum mechanics textbooks and you'll find the full description of the properties. What are the properties of wave function solution of an Hamiltonian with a given symmetry? They don't necessarily have that symmetry, but they have something else. In this particular case, actually here, sorry, this, you see it better here. If I translate, or I can do it directly here. Suppose that I apply to my wave function an arbitrary translational vector, right? I'm translating my Brevet lattice point. So I'm looking at what happens if I translate my wave functions now. If I translate the potential, it goes into itself. If I translate the wave function, what does it happen? The periodic part is periodic. So it goes into itself, right? R plus Ri is R, because it's periodic by definition. Now this one is psi of k, and this is a phase. Okay? For inversion symmetry, it was a minus. For this particular symmetry, it is a phase. So the function goes into itself, but not exactly. It acquires a phase. And that phase actually happens to be the eigenvalue of the translational operator. So there's no time for me to go into the details and to the full theory of the properties of the symmetry properties of wave functions, which are solutions of Hamiltonians with well-defined symmetry. Symmetry properties. There is a whole theory about that. I just want you to remember, to recall that the solutions do not necessarily have the same symmetry, but they have some important properties. In this particular case, this property is Bloch's theorem. So Bloch's theorem is precisely a statement about the residual symmetry property of the wave functions, which are the consequence of the translational symmetry of the potential. And it's essentially this statement here, or if you wish, this one. That is, the wave function acquires a phase which is proportional to the period that, to the amount to the vector we use to shift the function itself. Okay? So Bloch's theorem is nothing else than a rephrasing of an important property of the quantum mechanical solution of Hamiltonians with specific symmetries. So you can see it that way as well. Okay. Yes. Oh, we're here, okay. So if you take the limit of n going to infinity, well, not here, but in our discussion before, you said, okay? Yes. You want to see how the wave function changes? Yes, there's no change. I mean, you want to see how the wave function changes. There's no change. It's simply, you simply have to restrict the values of k to those discrete values. The wave function remains the same. The only difference is that the only allowed values of k are a discrete set of them, according to the discussion we had before. So this is not a continuum of points of possible values of k between minus pi over a, but it's a discrete set, and which becomes finer and finer the larger is n. In the limit of infinite n, it becomes a continuum of points. That's the only difference. The wave function itself does not change. What about where? Here? Here? Same. This is the only have to think that k takes discrete values. That's the only assumption. I mean, the only consequence of taking these periodic boundary conditions with large n. Okay, but that was just, I mean, a trick. We're now getting to a point in which this is now an exact statement. It doesn't rely on any tricks. Well, it does rely on some mathematical tricks, of course, but I'm going to give you only the final statement in general terms. We have proved it for a specific example, very simple one. This statement is now general because we are now in 3 dimensions. We now have a general potential, periodic potential, and this statement is now true. It's mathematically, I mean, true for this assumption, as long as those assumptions are correct. It is not for a finite system because here we're assuming that Ri belongs to a Bravais lattice, so this is not a finite system. Oh, I think I see what you're trying to. Okay, yes. The question you said that how can I then make my counting arguments and let n go into infinity? That's probably what you're trying to argue, I guess. You can always say that the following. This is for an infinite system. Then I can force my wave function. I can look for solutions of the problem where I'm imposing a periodicity, a real periodicity over a very large n. Okay, so instead of using this statement, I'm imposing a periodicity over a very large n, and then I will be able to count the numbers. So it's simply the same argument that we used before. Okay. Okay, so let's take a break. Let's take a break for the time being. Seems to be a lot of noise on the other side. Actually, let's do this. I think we can stop the lecture here because the next topic will be something that requires me at least half an hour to discuss. So I suggest that we stop here and we resume on Friday. It's a good point to stop.